We are going to start the solution of the problem of fluid-driven fractures by solving the problem of stresses around a pressurized fracture with constant pressure. The solution will also give us the displacements that are caused by pressurizing a fracture and therefore the width of such a fracture in the subsurface. This fracture is going to be pressurized with a pressure P within an elastic medium which is subjected to a least principal stress perpendicular to the direction of the fracture. In this case, we're going to start with a 2D problem or a plane strain problem. In order to make this solution a little bit easier, what we're going to do is we're going to decompose this state of stress by the principle of superposition in two different problems. The first problem is a problem that just involves the in situ stresses, and we could call it just a static problem with the background stresses with the least principal stress. I know how to solve that, so that's not going to be the emphasis of the solution. On the other hand, I'm going to have to solve also the problem, which is the stress and deformation induced by a pressure in the fracture in excess of the least principal stress. This is what we call the net pressure. For example, if the net pressure is equal to 0, and then that's going to be equal to the least principal stress, and there's going to be no action added into this particular solid. I'm assuming in this case that my solid has no permeability and no pore pressure and nothing in the pores. So we're going to start just with a solid. So in that case, if the pressure is equal to the far field stress, then nothing is going to happen. The fracture is not going to open. Okay, but that's a trivial solution. What about if the pressure is higher than the least principal stress and we do have a net pressure which is higher than 0? All right, we're going to see the solution for that problem in terms of the Griffith solution, and remember that we're just going to solve this part of the problem. Eventually, we might have to add this part of the problem for solving a specific problem, but now let's just take a look at the effect of pressure inside the fracture in an elastic domain. This is what is called the Griffith solution. Griffith solved the Navier's equation, and he solved this equation analytically for a linear, elastic, isotropic, and homogeneous solid, which means that the properties do not change with location. In this linear elastic solid, we have a fracture which is pressurized with a pressure P. In the general case, P could be a function of X. In this case, we're going to assume that P is a constant and the pressure along the fracture is equal just to a value called P naught. The fracture is immersed in an infinite medium with properties Young modulus E and Poisson ratio nu. And because this is an isotropic solid, then in plane strain conditions, I'm going to see that the deformation is going to be directly proportional to the, or actually inversely proportional to the plane strain modulus E prime given by this equation. All right. So let's see what the Griffith solution is. We're not going to solve analytically this equation. Griffith was quite good in math, and he did that, but we're just going to jump to the solution and understand that solution. First of all, if I have a net pressure, in this case, just called P, which is higher than 0, then I would expect a certain deformation in the fracture. That deformation and that solution is going to be the displacement of the wall of the fracture, either up for the top face of the fracture or down for the lower face of the fracture. In this case, let us just concentrate on the top face. And the top face, as the fracture is pressurized, will move from the center to a new position, and the displacement is going to be uy. Uy is going to be a function of where that point is along the fracture. And the solution, therefore, is going to depend on the position x. And at the fracture, that means at y equal to 0, then the solution is going to be the following. For any point outside the fracture, the solution is going to be, and that's actually also a condition, that there is no displacement. So this is going to be equal to 0 for any position x which is larger than the fracture half length c. Remember that in this case, I'm just analyzing a static fracture. It's not propagating, it's just being pressurized and it's being deformed. All right, the solution within the fracture is given by Griffith, and Griffith found that that displacement is going to be proportional to the pressure, net pressure inside the fracture, divided the plane strain modulus, and that kind of makes sense, right? Because the larger the pressure, the larger is going to be the displacement. The stiffer the solid, the smaller is going to be the displacement, times the square root of the half length squared minus the variable x squared. And all of that, as I was saying before, square root. And this solution is going to be valid whenever x goes from 0 to c. So within the fracture, inside the fracture. From here, we can get right away what is going to be the width of the fracture, and actually the maximum width, W naught. So W naught is going to be 2 times the displacement, because one face is going to go up and the other face is going to go down, at x equal to 0 and y equal to 0. And if you look at the solution when x is equal to 0, then this is just going to be, all of this is just going to be c. So 2 times 2p naught c divided by the plane strain modulus is just going to be 4 times the pressure times the fracture half length divided the plane strain modulus. So this is going to be the fracture width for a constant pressure in the fracture with a fracture half length c and a plane strain modulus E prime. Notice that in this solution, as we said before, the width is proportional to the pressure, makes sense. Inversely proportional to the plane strain modulus, it also makes sense. But now there is a new variable, which is the fracture half length, and tells you that the width is going to be proportional to the fracture half length. Within the same medium, with the same pressure, the longer the fracture, the bigger the width is going to be. And these are going to be linearly related. There is something else that we can get from this equation. We can get the slenderness of the fracture, the width divided by c, or actually that would be the inverse of the slenderness. But I just want you to keep in mind and to remember more or less what is the ratio of the width to the length. And if we were to bring this c over here, then everything we will be left with would be this part of the equation. Notice that typical net pressures are in the order of a few megapascals, and a typical plane strain modulus is in the order of a few gigapascals. So what this equation is telling us is that the ratio of width to fracture half length is in the order of 1 over 1000. So the width is going to be more or less 1,000th of the fracture length. And what this theory is telling you is that these fractures tend to be quite slender, with a length about 10 times, I'm sorry, about 1,000 times the value of the width. All right, we have addressed the first part of the solution, which are the displacements. Remember that when you are solving the Navier's equation, always you solve for displacement and then you compute your stresses. All right, let's look at what are the stresses around the fracture and what that solution is. And let's start for the region in which the pressure is in contact with the solid. Whenever the pressure is in contact with the solid, then the value of the normal stress, sigma yy, at the face of the fracture has to be equal to the pressure inside the fracture. So actually, at the wall of the fracture, this is a boundary condition that tells us that sigma yy has to be equal to the net pressure, or the pressure inside the fracture in this simplified case, for the region in which the variable x is greater or equal than 0, but also is smaller than the fracture half length c. So in all this domain, this is a boundary condition, something I am imposing. The normal stress sigma yy is going to be equal just to the pressure inside the fracture, which in this case is going to be a compression. And we're going to assume that that compression with this notation is a positive value. All right, what happens outside the fracture? Outside the fracture, what Griffith found is that the solution for stress takes the shape that you see over here, and the equation is what you see in this equation, in which I'm going to have a tension, and that tension is proportional to P naught times x divided square root of x squared minus half length squared, all of that square root, minus 1. And this is a solution which is going to be valid for x which is equal or larger than c. Let's analyze what that solution is telling us. First of all, it's telling us that we have a tension. And if, for example, we wanted to plug x equal to c over here, we will see that this is going to be 0. And c divided by 0 is going to be infinity. And we cannot deal with infinity. The equation tells us that we have a stress which is infinity, and mathematically that's correct, but physically it doesn't make a lot of sense to us. And this is the issue and why we cannot use tensile strength criterion when predicting the propagation of a fracture. Because if I use a linear elastic solution, the stress that I get, whatever the pressure is going to be infinity. And infinity is going to be always higher than any number of tensile strength. So this is why I cannot use the tensile strength criterion. This is not a finite number, and I cannot compare it to tensile strength. So we're going to have to use another solution for this, but don't worry, we have that solution. Before we go into that, let's notice a few things in this solution. As you get to the tip, the stress tends to infinity in tension, but it quickly decays as you get further away from the tip. So at the tip we have a tension, but then, for example, the solution tells you that at 0.15 of the fracture half length, you're going to find that the tension is equal to more or less 0.15. Is going to be equal to the pressure in the fracture, but with the reverse sign. And as you go further and further away, this tension is going to decay very quickly into an asymptotic trend to zero. Okay, so this also makes sense because it's telling us that in order to support this compression at the face of the fracture, I need a tension that is balancing that compression. And when I pressurize this fracture, that's going to be at the expense of a material getting in tension at the tip of the fracture. All right, so now that we have the solution for the Griffith equation, and let's add here that this is going to tend to negative infinity. And remember that here in the graphical solution, I'm putting two sides of the fracture, and in the equations we just have one side, but it's the same thing. And let me just add a few more things. So here, this is going into compression. This is going into tension. All right. Let's see how we solve this problem of having a stress that goes or tends to infinity at the tip of the fracture, and how we can develop a criterion to see if the fracture is going to propagate or not. In order to do this, we're going to appeal to what is called the stress intensity factor. The stress intensity factor, Ki, is defined as the limit of the product of the square root of r, where r is a variable which is defined as the distance from the tip, times the stress at that particular location. So let me go a little bit up in here, and probably this is a better image to to talk about the stress intensity factor. R is going to be a variable that starts at the fracture half length and increases from there. So this is going to be R. So what I'm going to do is I'm going to multiply a quantity R that tends to 0 times a quantity sigma that tends to infinity. And mathematically, I cannot do that. I don't know what the limit is for something, for a product that's something that goes from 0 to infinity, but I'm going to use some mathematical tricks to get this limit as a defined quantity. Before we go ahead, let me mention a few things. Here we're going to talk about the stress intensity factor K1 or Ki. This is the one which is called the open mode fracture, or a stress intensity factor for an open mode fracture. An open mode fracture means that I have a material in which the fracture is being done by opening the two sides or the two faces of the fracture. This is open mode. There are other two modes of fracturing, and also two other definitions very similar to this one of the stress intensity factor that apply to a fracture shear in plane and shear out of plane. In the fractures for shear in plane, what I have is something similar to what I'm going to draw right now, in which I'm pushing on one side, pulling from the other, and at the tip of the fracture right here, I'm creating I might create also a stress intensification that might produce this fracture to propagate. And shear out of plane is a little bit more difficult to plot, but let me try anyway. It's something like this, where what I'm doing is, wait a minute, this always causes me trouble. So let me try again. is going to be, okay, I think I got it. It's going to be the type of fracture that you have when you have this type of action on the tip of the fracture, where the tip is right here. So this is the shear out of plane. A little bit exaggerated here, but I hope that I'm making the point. What we're going to talk now is about the open mode, K1 or Ki. So I was telling you, in order to arrive to this stress intensity factor, then I'm going to use a few mathematical tricks in order to calculate that limit. First of all, I'm going to replace here the equation of sigma yy for what I have over there. And I'm going to also replace a variable x by what x is in terms of the fracture half length and the variable r. Remember that the fracture half length is this. So x is actually equal to c plus r. And the next thing I'm going to do is to get out of the limit the constant quantities like square root of 2 pi and p naught. And after I do that, I'm going to take this radius and multiply it to these two quantities. And as I do that, and you may want to check that on your own, when r goes, for example, multiplied by 1 and r tends to 0, that's not going to cause me any trouble in the limit. And the same here, as r to the 3 over 2 is not going to cause me any problems as that goes to 0, but that's going to simplify the denominator. And it's going to simplify it in a way in which the r is going to, this r is going to cancel out, and here this r is just going to tend to 0. So as that tends to 0, the only thing which is going to be left is going to be c over square root of 2 times square root of c. And that's already taken the limit. And since I can simplify a little bit this equation, I'm going to find out that the stress intensity factor for a linear fracture pressurized with constant pressure is going to be what I see over here. And remember that this is going to be for a constant pressure. Sometimes we have cases and in which the pressure is not constant and the stress intensity factor is going to be a little bit different. Remember that for the coupled problem of fluid fracture propagation, the pressure varies along the fracture as it goes from the wellbore to the tip of the fracture, so this pressure is not going to be constant. Nevertheless, we're going to find that this equation is going to be very useful to us in developing some simplified models that capture fracture propagation. All right, so now that I have this type of criterion, I can establish whether the fracture is going to propagate or not. And notice that all of these are finite quantities like p naught, pi, and c, which is a fracture half length, and I have everything I need. One more thing here, before we go into typical values of the fracture toughness, notice that the stress intensity factor depends not only on the pressure inside the fracture, but also very importantly on the length of the fracture. And what that means is that, for example, a fracture which is short with a given pressure might not propagate, but the same fracture in the same medium, but starting at a longer length, is going to propagate with all the same conditions just because of the length. So the longer the fracture, the higher is going to be the stress intensity and the easier it's going to be for those fractures to propagate. All right, so the criterion here is going to be, let me add a little bit more of space, that this is something that we mentioned before, but anyways, we're going to to repeat this because it's something very important. The linear elastic fracture mechanics criterion for fracture propagation is going to be the following. We said, remember that we cannot use tensile strength. So what we're going to use is the stress intensity. Whenever the stress intensity, which depends on my fracture length and the pressure, is higher than actually higher or equal than the toughness of the rock, which is a material property that we're going to talk about in just a minute, then this implies fracture propagation. These are two finite quantities and I can compare them. When the intensity is less than the fracture toughness, then there is no fracture propagation. You may ask yourself, what is this C? The C comes from critical. So this quantity called the fracture toughness is a property that characterizes the material, and the C comes from critical. The fracture toughness is the critical stress intensity factor for which a fracture might start to propagate. And let me add one more thing over there, something that we're going to revisit later, but will be also useful to incorporate into our concepts. If I were to track the velocity of fracture propagation, and let me add, for example, units just to make sure that this is a velocity, and I compare this to the fracture intensity, what is often observed is that at the critical fracture intensity, there is a significant increase on the velocity of the fracture. Just assuming that without involving fluids, without involving injection rates, just talking about linear elastic fracture mechanics in a solid, as the stress intensity approaches the critical intensity value of fracture toughness, the velocity quickly increases and tends to a very high number. So what I'm going to say is, whenever my intensity is higher than the intensity, the critical intensity, then I have fracture propagation. Whenever this value is lower, I notice this, and we're going to come back to this. There might be also fracture propagation, but it's going to be very, very slow. And this is something called subcritical fracture propagation. We'll come back to that later on. All right. But for now, let's just keep in mind this basic criterion comparing stress intensity factor to fracture toughness or critical stress intensity factor. So the only thing we have to do now is to complete the discussion about what fracture toughness is and how we measure that. And this is measured to tests in which we usually have a notch, which is a pre-made fracture. And typical values for KIC or K1C go for geological materials, including rocks, in the order of 0.2 MPa times meter square root to 2. Notice this weird unit. Probably if you weren't familiar with stress intensity factors, you never saw it before, but notice that it comes right away from the definition: a pressure times a length square root. And the way that we measure this fracture toughness is it can be done in the laboratory. There are several types of these notch experiments, but one of them, which is very popular in geomechanics, is the semicircular bending test. in the semicircular bending test, what is done is to subject a rock sample, semicircular rock sample with a pre-made notch, to a loading. By assuming linear elasticity and isotropy in this solid, I can relate the stress intensity factor and eventually the stress intensity factor over here in the tip at which the rock fails to the load applied and the geometrical conditions. And the solution for that is right here. For example, this is the fracture toughness as a function of the force applied, and as a function, notice here the length of the notch, in this case called A, and other geometrical factors. But this can be done in the laboratory, and it is actually done. And it is how many times fracture toughness is measured in the laboratory. So with this discussion, then we see that thanks to now linear elastic fracture mechanics, we do have a fracture propagation criterion that does not rely on tensile strength, but rather relies on fracture toughness. And very importantly, that also now we can calculate the width of the fracture as a function of pressure.